Yeah.
Half of 11.
Yeah.
Because
Of course, of course.
I have a appointment with a doctor emergency, so.
Yeah. No, of course, of course, of course. That's also why we've got the video, right? We're all grown-ups. Okay, so let's think about how our household is going to choose how many CI to buy. How is it going to assemble its basket? How is it going to put together its wardrobe? Right? I think we know this intuitively. On the one hand, I told you our household would like to have, as we would, a little bit of color. No one wants to have. Imagine if you wore the same clothes every single day. Kind of have a little bit of variety is the spice of life. a preference for variety. But intuitively we understand that if something's more expensive, we're probably going to want less of it. We're going to try and substitute something else for it. All right, so we've taken these goods, we've normalized them, as I said, at the interval. I think of it, we're just calling each good, we're giving it a number, and it's a number between 0 and 1. This also gives us a nice way to interpret things. We're going to see that the aggregate consumption good, here, this basket, is going to be, and think of it as an average of these goods. Because we're also normalizing these goods on the interval 0, 1, a lot of the quantities that come out can be thought of like our aggregate price level is going to be the average of prices of individual goods. Right, so this epsilon is the intra-temporal, so within a period of time. Right, so it's the elasticity of substitution between the differentiated goods. Right? Or, and we'll see this in a minute here as well, the price elasticity of demand. Right? Elasticities, right, are useful. They tell us the percentage change, say here, in the demand for good. Oh yeah, J. If its price goes up by 1%, for example. So it's percent. Right? It's difficult to otherwise we have these units floating around that are always problematic. Right? If the price of this water goes up by 10,000 dong, by how much will your demand per year go down in terms of bottles of water? Okay. So we have when I say a price change, your brain, what it's doing is you're looking at this price. So how much does this cost? Is that a large price change or a small price change? If I say 10,000 dong price increase, it depends on how much the object already costs. That would be a significant price increase for a bottle of water. If I say this cell phone, the price has gone up by 10,000 dong, well, that's barely a price change at all, right? You're already thinking relative to what the price level started out at, right? So you're thinking intuitively in terms of percentage changes. And then in terms of quantities, comparing liters of water to units of a cell phone to, milliliters of gift, right? It's difficult to compare, like what is more, what is less. This doesn't, I think I use a lot more water than this spray on a daily basis. So, changing a 1 liter purchase of water isn't a big deal. I'll drink that in a day. A liter of this is probably going to last a semester or two, right? That's why we like to think in terms of elasticity, right? It's going to be normalized by the quantities, normalized by the price. So we think of percentage change in, percentage change out, right? We don't have to think about the units, right? Okay. And then we can define this. We can also derive it from this setup, but we can define the price index as here this weighted sum, right? Now you can think of there's different ways to take or to calculate an average. You can think of an average, so let's say we have average of x1 and x2. arithmetic. All right, we also have a geometric average. All right, so you can think, let's say, if x1 equals 1 and x2 equals 4, this would be 2.5, and this would be 2. We also can write a yeah, it doesn't matter. Right, and this sort of, think of this as a sum, or these powers. Right? We can write this more generally as the product of xj 1 to n, the power of 1 over n. Yeah? This is x1 to the 1/2 times x2 to the 1/2. Yeah, and that's essentially what we're doing here. We're doing a geometric average. All right, and they have some nice properties here. All right, you can also look at if x1 equals x2 equals, let's say, 2. We get 2 plus 2 is 4. This is equal to 2. 2 plus 2 is 4. Square root of 2 is 2. All right, so you're going to see there's some we have slightly different results. Geometric. Oh, that's the one I want. Yeah. We can also write a harmonic mean. This will show up in it's going to be n over the sum xj 1 over n. All right, so here this is right. Yeah. Right. All right. So you see some similarity there, and that would give us, in this case, we would have 2 over 1, so it's 1 over n, so that's 1 square root plus square root of, no wait, that's not quite right. What did I do there? No, it's just that's the sum, sorry. Right. Yeah. So this would give us 3/2. Bring it up here. This would give us then 3. In this case, if we have 2, for both of them, this would give us 2 over. So notice the property, all these different definitions of the mean, when all the numbers are the same, you get the same answer, right? Right, and we see, right, so when they're different, right, there's going to be some different weighting, right? All right, so this price index, it's just an average of these individual prices. All right. So we want to determine now our optimal demand for a single good. So we're going to allocate our consumption expenditures among these different goods. So we're going to do this, we're going to find the allocation, the division of sum of any given expenditure level, ZT, to solve the following problem. So we're going to maximize, our objective is to maximize this consumption basket. We want to make the best possible wardrobe, subject to the fact that we have to buy, right, pay for all of the components, all of the clothes that we put into our wardrobe, and we're going to limit our budget. So it's kind of like, just think of this, I'm sure there are reality TV shows that work like this. Someone says, here is 10 million dong, so Z, put together the best wardrobe, right, for for the summer or something like that, right? And so now you have the task. You have to go down to Ho Chi Minh City. You have 10 million dong, and you're supposed to put together a wardrobe, right? So I need pants, I need shirts, I don't want them all to be the same. We have some difference, some variety. So you're going to assemble a wardrobe with a fixed budget, right? There might be some things that you really like that are really expensive, so you're only going to buy one of them, right? Maybe there's something that's easily substitutable, like socks, maybe. Maybe you're a sock person and socks are really special to you. That's fine. I'm not, so I'll just buy the cheapest socks, right? I'm gonna try to save some of my ZT. I'm gonna buy lots of cheap socks so that I have more money for the shoes, right, or the shirts, right? So we're going to try to assemble the best possible wardrobe with a fixed budget ZT. Yeah. All right, and now let's maximize, right? So again, let's take a derivative, right? Let's take some derivatives. That's our secret here in economics. And this is a little confusing, perhaps, the first time you look at it, because we have this differentiation through the integral, right? And we have lots of outside-inside derivatives. Yeah? So let me define just for a second. Let me define xt equals this sum of CTI, this integral from 0 to 1 of CTI epsilon minus 1 over epsilon di, and yt equal to this sum from 0 to 1 of pti cti di. Then, right, our problem is max CTI xt epsilon over epsilon minus 1 minus lambda t yt minus zt. All right, well, now it should be maybe pretty straightforward. We're going to have an optimum. We're going to differentiate this with respect to some good CTI. We're trying to figure out how many black socks are going to be in our wardrobe. And we're going to pick out one good, or how many pink sweaters. Just some good in our wardrobe. And if we're optimizing with the optimal number of socks, black socks or pink sweaters, right, our objective function should be equal to 0. Right? We've optimized our wardrobe. We can't make our wardrobe any better if we buy more or less black socks. Well, xt is a function of CTI, so I'm going to take the derivative. I need to take the derivative, find the derivative of xt with respect to CTI. First, I'll leave that implicit. So let me take the derivative with respect to xt. So bring the exponent down. Subtract 1 from the exponent. All right, nothing difficult there. And then xt is a function of CTI. So from the chain rule, then it's the derivative of xt with respect to CTI. Minus lambda t times yt is also a function of CTI, times the derivative of yt with respect to CTI. Okay, all right, we learned how to do this many, many years ago. That's the easy derivative. Fantastic. So we just have to figure out how does x change with CTI and how does y change with CTI. All right, and let's start with y first. So what is this sum really? Right? What does it mean to differentiate under the integral? To intuitively, right, just remember this is like a sum. So think of it as yt is equal to the sum of different pt I CTIs, right? I don't know. So we're going to have pt 0.1 times ct 0.1 plus pt of good 0.2, ct 0.2, and so on. And so when I take the derivative with respect to any single one of these, so the derivative of yt with respect to, let's say, the good ct 0.2, well, that's the price of good 0.1, so that doesn't change. It only shows up once, and it's multiplied with its price. So this is going to give me times pt is equal to the price of the good 0.2. So going back here, when we take the derivative of yt with respect to CTI, that's for some individual good CTI. So we're integrating here. We could also write this as over all goods j, and now we want to take the derivative with respect to one individual good. Let's call it CTI. That would be like, give them all numbers and take the derivative with respect to one specific number. Well, the only thing we have is its price. So this is equal to PTI. All right, well, this is then similar for xti. We have the sum. We have ct 0.1 to the power of epsilon minus 1, ct of good 0.2 to the power of epsilon minus 1 over epsilon, and so on. So when we take the derivative with respect to an individual cti, right, we're just going to bring the exponent down. The derivative of xt with respect to some cti. We bring the exponent down, and we have then just that individual good. Every other good in the sum, this integral, doesn't change. Right, so its derivative is 0. So the only thing that we're changing is cti, and we subtract 1 from the exponent. And here we notice that with this exponent, minus 1, we can write this as minus epsilon over epsilon. So we're left then here, we can write this as epsilon minus 1 over epsilon, ct I to the power of minus 1 over epsilon. Right, and that exponent then likewise subtracting 1, that's subtract